Okay, welcome to lecture here. We're continuing on talking about electrochemistry in this chapter. Move a couple of things around. Okay, so we've been talking about electrochemistry, which again, as we talked about last time as well, is essentially redox reactions. Again, being oxidation reduction reactions. We went through again how to assign oxidation numbers, balance sort of redox reactions in both acidic and basic conditions using water to do so. And then we kind of tied it into really kind of the main topic of sort of this chapter, which is galvanic cells. And galvanic cells really are just a redox reaction that's sort of set up traditionally in sort of laboratory, for example, using some beakers, using some solid electrodes. And there's several parts to the galvanic cell that we talked about last time, which are really important. We do have usually on one side, and we oftentimes draw it on the left-hand side, but it doesn't always has to be on the left-hand side, obviously, which is the anode compartment. And within the anode compartment, you usually have sort of a solid electrode that's sitting there. And, for example, say that zinc, as we maybe talked about before, that would mean that the solution that you pretty much have floating around, as we also talked about before, would contain basically the ionic version of sort of that solid electrode. Usually it's sort of connected through a wire, kind of goes through like a voltage meter, so you could kind of figure out the voltage of your cell. And then it will sort of drop out into the other side where, draw a beaker around that guy, where we would have, again, another sort of electrode over there, let's just call it copper, for example. And again, in the solution that's floating around, you again would have your copper ions floating around, be it in a solution of, say, copper 2 nitrate, copper 2 sulfate, that might be zinc nitrate, zinc sulfate, and so forth. And this is our cathode side. And within these sort of galvanic cells, two of the redox sort of properties basically are occurring. We have oxidation occurring over here at our anode side. Oxidation, again, meaning basically losing electrons. So what we see is they start to lose electrons sort of traveling via sort of a potential difference, if you will, on the other side to our cathode side, where basically reduction takes place. Remember that basically when that zinc electrode, for example, will lose electrons, it's basically going to kind of transfer from the solid, which is obviously in the beaker, into the liquid and basically become ions, right? So when things lose electrons, become positively charged, or things that are ions are typically the guys that are floating around in a solution. Those electrons, again, like I said, will travel across, basically come into sort of this solution over here and combine with the copper that's in the solution. And that's where our reduction reaction is going to take place. That's then going to create that guy that's in the solution, essentially sort of coming out of the solution, clearly not out of the beaker, but onto like sort of the solid there, electrode in that case. And that's sort of the redox sort of process that's occurring. And again, there's sort of a potential energy difference over here on the cathode side, more positive, you can think about it, again, going to kind of pull those electrons over. Now, as we talked about before, if we just sort of let this cell run like this with sort of nothing connecting the two, as you can see on the left-hand side, we really would get a buildup of positive charge happening. On the right-hand side, we'd actually get a buildup of negative charge happening. And you may be wondering, like, where's the negative charge? Because this solution, for example, maybe, like I said before, is maybe copper 2 nitrate, which means there's also something like nitrate floating around in here, which means if those electrons keep coming in and taking out the copper, the positively charged ions, you're going to build up a more negative charge. And by the way, there's perhaps something like sulfate floating around in here. But on this side, on the left-hand side, we're really building up more and more of that positive charge that's happening. So to prevent sort of that buildup of, I would say, incorrect in that sense. Charges are charges you really don't want in a galvanic cell situation, because remember, if we happen to let this roll this way and we build up that kind of negative and negative charge happening over here, eventually those negatively charged electrons are not going to want to continue to kind of come to the other side. So that's why usually we have this sort of salt bridge that's here that connects the two. And really the salt bridge, as we saw last time, it contains some type of ionic compound, like a soluble ionic compound. Like I think maybe they were using potassium chloride or sodium chloride or something like that. Even like sodium nitrate. So I think in the example we looked at, they were using potassium chloride. Potassium chloride obviously is potassium ions that are positive, chloride ions that are negative. So what we end up getting is the positive, for example, potassium would go this way, and the negative chloride would go this way. Sort of diffuse through, there's usually cotton balls to keep sort of that solution in there, allowing sort of a slow migration of those sort of ions to the correct side. Again, remembering we're building up a positive charge here, that's going to kind of pull those negatively charged ions in the salt bridge that way. We're building up a negatively charged on the right-hand side, that's going to pull the positively charged sort of potassium ions that way. And again, because it's not fully open, obviously it won't kind of all fall in. So it allows sort of a slow migration of those sort of ions into each side. Again, ultimately kind of keeping the overall charges where they need to be on each one to keep those electrons basically continuing to flow. Now, when we look at this sort of galvanic cell, it's important to remember that anything really can be an anode, anything can be a cathode. It just means whether or not you'll sort of get a galvanic cell that will work sort of properly or be sort of spontaneous. Now, we also saw that we can write things like for example, cell diagram. A cell diagram sometimes represents a galvanic cell and is sort of a shorthand for the cell that's going on. So my made up one here, we have our zinc solid going to our zinc with a +2 charge. And that's in our anode compartment, basically, right? We have our zinc losing electrons, becoming zinc 2+, separated by the salt bridge, which is basically what those two lines represent, going to our copper, which is starting with a +2 to our solid copper here in this particular case. Again, sometimes we will write, and this would be our cathode compartment, if you will. And sometimes we do write things like the molarity in here, like with 1 molar. You know, if we have some type of gas, we may do something with atmospheres or pressure sort of included in there as well. And that cell diagram, again, represents sort of what's going on in this sort of galvanic cell that I built here on the screen. And how do we translate that into sort of the reaction that's taking place? So usually, again, these cell diagrams are set up this way, which means that how they're typically set up is the first thing there is your reactant, second thing is your product, first thing on the other side of the salt bridge, reactant and product. So if we were to write sort of the reaction that goes with this, we would sort of follow that sort of rule. Zinc is a reactant, so then would be copper with a +2 charge going to our zinc with a +2 charge, which is a product, and our copper with a solid charge here. And again, that shows our overall reaction that's sort of taking place. We also then got into sort of a conversation about sort of what are referred to as Srp values. Srp stands for standard reduction potential. And it's basically, these are sort of basically table values that you would look up as we sort of touched upon. I think sort of where we kind of left off last time was with this idea that when we go to this table and look it up, these values, which were basically made by using a standard hydrogen electrode, where they gave it, again, a value of 0 volts. these are all going to be reduction reactions. And as we know, with a redox reaction, actually both things always take place. There's always an oxidation reaction and there's always a reduction reaction, which means that when we go to the table, essentially one of the reactions are written incorrectly, and technically speaking, one of the signs are also incorrect for that particular guy. But we can calculate the E of the cell or the cell voltage by using one equation here, which is E of the cell is E of our cathode minus E of our anode. And the conversation we had at the end last time was about this equation and really more so about the subtraction part. And the subtraction part's here for an important reason because it will actually fix the problem for you in terms of the calculation of you have sort of the wrong sign on it. So, I think we were looking at maybe, the zinc. If you looked up that zinc in the table, it would be Zn plus a couple of electrons, gives you Zn solid. And the E naught that you would find in that table was minus 0.76 volts. And if the zinc was in our galvanic cell, the cathode, then this reaction and this E value is perfectly good, right? Because it technically would be our cathode. But in this example, as we can see, it is technically not our cathode, it's our anode. And this reaction is not written as an oxidation reaction, it's written as a reduction reaction. And that's why they are all written as reduction reactions, because they're Srp values. So technically speaking, to turn this into an oxidation reaction, so this guy here, right, is a reduction reaction. To turn this into an oxidation reaction, we basically would need to flip it, and that would give us zinc goes to zinc with a 2 plus and a couple of electrons. This has now become an oxidation half reaction. And if we do reverse these reactions, which is essentially what we did, we just kind of flipped everybody around. What happens to the sign of our E will now become positive 0.76 volts. This is no longer a standard reduction potential. This is kind of like a standard oxidation potential, like SOP, standard oxidation potential in this particular case. So the correct sort of E value for the oxidation reaction is actually this one where we change the sign. And that's, again, all we did is basically change the sign. If you were asked to write the half reaction for the oxidation half reaction and what the E value was, and you wrote minus 0.76 volts, it technically is the wrong answer. Minus 0.76 volts is for the reduction half reaction, not the oxidation. So because of that, and because sometimes people would like to sort of rearrange the equation and change the sign, which is perfectly fine to do, and some people might even say it is sort of the correct thing to do, you should take this equation and not subtract, but you should add. So you'll sometimes see, again, two versions of this equation, one where we subtract and one where we add. The one that you would want to use when you would add is if you yourself decided to change the sign of that. You would not add them if you decided not to change the sign, which is actually perfectly fine as long as you use this equation. So what I'm going to just show you is the back part of this equation on both of them. If you did E of the cathode minus E of our anode and you got it from the table, technically you did not change the sign, so it would be minus 0.76 volts, gives us a positive 0.76 volts on the back end of the calculation, obviously still minus the cathode. Now, if we change the sign here, we end up with E of a cathode plus 0.76 volts. So you can see it comes out the same no matter which way you do. And that is why there is a negative here, our subtraction button, because it will sort of automatically change the anode value into the correct sign for you. So as I think we finished up upon last time, I mentioned that you probably should sort of pick one way and stick with it. either decide you want to not change the sign and subtract, or decide you want to change the sign and add. As I think I finished up on last time, don't do both. Otherwise, again, you may obviously be undoing the changing of the sign. Any questions on that stuff that we talked about last time? Here's another one, and remember, using our standard hydrogen electrode, or sometimes referred to as the She, as the standard. If we hook it up now with copper, we get a cell voltage. This also demonstrates something I was just talking about. In the previous example, our hydrogen electrode was the cathode. Here, our hydrogen electrode is actually going to be the anode in this particular case, while our copper will be the cathode. So you definitely can kind of pick and choose and make anything the anode, make anything the cathode. It just depends on sort of the combination that you put together as to whether or not it will sort of work, or it will sort of give you a good cell voltage. By doing so, we could see here, we could get the reduction potential of copper, which in this case is 0.34. And again, here we have our anode, where this guy's going from 0 to +1, right? Losing electrons in our compartment and our cell diagram. And over here, our cathode compartment, we see our copper going from +2 to 0, gaining electrons and going through reduction. So again, our anode and our cathode in this particular case, and our overall reaction on the bottom that represents that. As we also talked about last time, again, sometimes when you're using sort of an anode or a cathode that maybe doesn't have a physical presence, we sometimes will use something like platinum here as sort of the physical electrode that kind of connects everything. We also see, because hydrogen is really a gas, we have some insertion there of some pressure into our cell diagram, as opposed to a concentration like it is on that side. So where do we sort of see all these numbers? We see all these numbers in a standard reduction potential table, such as this one. You have a similar one in your book as well. But what we see here again is, because it's that SRP, there are all reduction reactions, which again, this is the table I was referencing before, our table like this, that you would go and look up the values. You want to make sure when you go to a table like this that you look up the values, carefully. And what I mean by that is, you want to make sure that the half reaction you grab is actually the one that you're looking for. Like, it's going to the correct sort of outcome. And what I mean by that is, for example, you may look on this table or a table like this, and you may see something like iron, where it goes from iron 3 to iron that's solid. You may also find one that has iron 3 going to maybe iron 2, which may not be the right one that you're looking for in this particular situation. We see a couple of things here: stronger oxidizing agents as we go up on this table, reducing agents getting weaker as we go up on this table. Stronger oxidizing agents towards the top here. These are our Srp values coming through here. Here's hydrogen as well, with our sort of Srp values. And again, you want to make sure that when you look up these things, you do sort of get it. Here's a chromium, for example, another example of that. This is chromium 3 that ends up at chromium only 2 over here, I believe. So you can, if that's not really the one you're looking for, you might want chromium going to chromium solid with no charge. So there are some different entries in these type of tables of the same sort of ions. So you got to make sure that sort of your reactant and product is really what you're looking for, and not just sort of pick the first one that you see sort of in this table. As we've talked about, again, because these are all reduction potentials, technically speaking, we do need to reverse, one of those sort of reactions to make it sort of correct. And again, if we were doing something like, hang on here, let's say we were doing something like, speaking of that, we'll do, iron and say cadmium, and let's say we add our iron here. Oops. Actually, let's go back this way then. We'll do it that way. Iron to iron 3 in our anode compartment, and then maybe we'll do some cadmium to cadmium here in our cathode, right? So this is our cathode, this is our anode. So again, if we went to the table here to look up those two values, we'd find our cadmium, where are we at there? Right here. So if we just took the cadmium reaction and wrote it out, we would have it from the table. It looks something like this. And in this particular case, getting old, but looks like minus 0.4 volts is our E. If we look up our iron, which we'll do iron 3 in this case, which is right here, we would take it from the table here, Fe 3 plus 3 electrons, make some solid iron over here, and our E of that guy is minus 0.036 volts. Now, these are both reduction reactions, but we know in our case that the iron is actually our anode and the cathode is our cadmium. So if we were going to use the equation that we saw earlier just the way it was, which would be, again, E of our cathode minus E of our anode. And the only thing that we really want to know was what is the E of the cell or the cell voltage. We can simply go to this table, find those two E values, determine which ones are cathode and anode, and put it in there. So again, in our case here, the cadmium was our cathode, which is minus 0.4 volts. Minus, again, I'm not going to change the sign of my iron, even though technically I should. This is going to be minus 0.036 if I didn't lose a zero there. And again, that subtraction is actually going to change the sign for us, and we will end up with minus 0.40 minus R minus 0.036. Going to give us a minus 0.36, I'll just round volts for our cell. Now, this would be a situation, again, where you just wanted to go to the table, you just wanted to kind of pick it up and figure out, you know, what is the cell voltage. If I wanted to actually sort of write these reactions correctly, my cadmium is correct because it's a cathode reaction, it's a reduction reaction. So my cadmium reaction would be the same. Which means that my E of this Srp value would be minus 0.40 volts. My iron is actually backwards. I need to reverse this to make it into a anode reaction. And if I do that, flipping it around, put the solid iron over there, the iron with a +3 charge on the product side, and my 3 electrons. When I do that, I then should change the sign that I find in the table. In this case, going from negative to positive, and we would have positive 0.036 volts. This is actually the correct number that goes with this oxidation reaction. If I did that, this again is the case where we would want to add and not subtract, because I already done this changing of the sign by myself. So I would add it now to positive 0.036 volts, giving me the same 0.36 volts when it's all said and done. So again, if you decided to flip the sign and change it, we want to add and not subtract. If you don't want to worry about flipping the sign, you then just subtract. By the way, I can now add these together, but it is still a redox reaction, which means I cannot add these together because we have different numbers of electrons. So we do need the same numbers of electrons. I would need to multiply the top half reaction by 3. I would need to multiply the bottom half reaction by 2 to make sure that we do have the same number of electrons. And if I did that, I would end up with 3 cadmiums plus 6 electrons goes to 3 solid cadmiums. On the bottom one, multiplying by 2 would give me 2 irons. Goes to 2 iron 3s and 6 electrons. At this point now I could properly add these together and get my balanced overall redox reaction that is occurring in this case. Kind of similar to a regular redox reaction here. Making sure I have an extra D in there. There we go. 3 cadmium plus 2 iron 3s here. And basically this would be my balanced redox reaction in this case. The cadmium again going from +2 to 0. Gaining electrons are iron going from 0 to +3, again losing electrons and being oxidized. You may ask, does multiplying by these coefficients to get the correct number of electrons affect these E values? And the answer is actually no, it will not affect the E values. So you can multiply by as many as you want. The Srp value that you find in the table actually will be unaffected by that. Any questions on that? Okay. Here's another table, which you could clearly see everything in this table with a magnifying glass, I suppose. But let's talk about some important things, some of which we sort of touched upon at this point, but just to make sure, when you look at this Srp table, and again, this is obviously another Srp table from another book, but they're all basically the same sort of tables. The E naught that you see for the reaction is technically for the reaction as it's written. So that's what we were talking about here, where technically speaking, if I wrote like I did here, this reaction for my iron that came out of the table, which is the reduction reaction, the E value should be this. If I do the correct thing and reverse the iron one in this example, which is the oxidation reaction, we really should quote the E value as being the positive version. So really, you know, the value of E that you sort of quote should really complement the reaction that you see. Now, the more positive E value that we see on the table, the greater the tendency is for that substance to be reduced. So this is a very important thing in terms of determining, you know, you may be thinking, well, how do I know which one's going to be my anode and which one's going to be my cathode, right? It's like, I got these two things, I'm going to build the cell, you know, which one should be the anode? Which one should perhaps be hooked up as the cathode? And this can really help you do that in the absence of any other information in a problem. Like they don't give you the reaction. They don't give you, you know, specifically say, this guy's your anode, this guy's your cathode. They don't give you the overall reaction. They just simply say, hey, you made a cell out of these two things. You can go to this table and you can find which one of those two things is more positive. When it's more positive, it has a greater tendency to be reduced. So when we think about anode and cathode, what happens in each of these locations? Anode goes through oxidation. Cathode goes through reduction, which means the more positive one is the one that gets reduced. So you can look at the values, and typically speaking, when you go to the table, again, in the absence of any other piece of information given to you, the one that is more positive should be your cathode. Now, let me be very clear that if they do give you a reaction or tell you how something is happening, you do need to look and see what is being oxidized and what is being reduced, and that will determine, you know, which one's your anode and which one's your cathode. But they really don't give you any of that information. Then you could go by the one that's more positive. The half cell reactions can be reversed, as I just showed you on the previous slide. And when we do reverse them, we take, technically speaking, the sign that we find in the table and we change it, basically, because we reversed it. So again, you know, if you grab any of these out of here and you decided that, say, silver is going to be from this table here, if you look up silver, it looks something like this with the E value of Srp value really of 0.80, and I believe it's positive. Getting old, but I think it's right about there. And again, if this case, the silver was not our cathode, but it was our anode, we would need to reverse that reaction. And again, what it would do to the sign is that for this guy, the correct E value would be minus 0.8 volts. So again, we could change the sign. If I did that and I wanted to figure out E of the cell at that point, I would add and not subtract. The last thing down there, as we just saw when I did that last equation, you can multiply the half reactions by coefficients, and it will have really no effect upon those values that we see in the table. So those are not changed. So that's kind of different than a lot of things. Sometimes when we deal with, say delta H or something like that, if we multiply across, those values also get multiplied. Any questions on that there? Okay, so why don't you try one here and see what you come up with. We'll give you a couple of the Srp values that you would find here. Why don't we do a couple of things here? Why don't you write the balanced equation, which is a little bit more than what they asked for. So write the balanced sort of redox reaction that's happening. Why don't you also do the cell diagram. Why don't you ID the anode and cathode? And obviously, like it asked, why don't you calculate the cell voltage? Cell voltage is basically what they're asking for here when they say standard EMF. All right, so take a few minutes here and sort of come up with those guys and see what you end up with. Let's take a look at it here. So first off, it's a good idea to try to figure out, what is going on in terms of what's our anode, perhaps, what's our cathode. That obviously will help us sort of do the calculations, if you like. So first off, looking at this, they basically just tell us we made pretty much a galvanic cell out of basically cadmium and chromium here. They didn't give us any other information other than that. So in this particular case, we would look at our Srp values. And again, these are the Srp values that you would get from that table we were just looking at. And when we look at this, we do see that this guy here is more positive, right? Even though they're both negative, but that's more positive of the two negatives. So by doing that and seeing that guy's more positive in this case, and again, they didn't give us any other information, we can make a pretty safe assumption that the cadmium here should be our cathode, and our anode here should be our chromium. That also means that this is where oxidation should be occurring, and this is where reduction should be occurring. So since we want to write the balanced equation, we do know we do need to flip the chromium around. The cadmium could actually stay exactly the way it is because it is written correctly here. And the E naught would technically be minus 0.4 volts. The chromium does need to be reversed because it is not written as an oxidation reaction. And if we reverse it, we will now turn it into an oxidation reaction. Technically speaking, the way that I just wrote this equation means that my E value should now change signs, and it should become positive 0.74 volts. I am almost ready to add this together, but we are going to run into the same situation that we talked about in the previous one I just did. We don't have the right number of electrons in each of these. So we do need to multiply these half reactions by, in this case, 3, in this case, 2. And I'm just going to rewrite those underneath it, obviously multiplying those guys across. So multiplying the top guy across going to give me 3 cadmiums in this case, plus our 6 electrons and our 3 cadmiums here. Our E naught, again, not going to be affected by that multiplication, still stays the same. Multiplying our 2 across the bottom there, put it in the states as well. Also, our value here not going to be affected by multiplying that. Now we're good to go. We can multiply these together, and not multiply them, but add them together. Electrons going to cancel out like they should in this redox reaction, and we will end up with the correctly balanced, really, redox reaction here that's happening in this cell. Again, keeping everything on the left-hand side stays on the left of the arrow. Everything on the right-hand side stays on the right-hand side of the arrow. And this would be, again, balanced reaction that's taking place. 3 cadmiums on both sides, 2 chromiums on both sides. Overall charge on the left, +6, and overall charge on the right, +6. It is balanced. First off, any questions on how to get to that reaction there? Also, a couple of things just to note, which will be important a little bit later on in some formulas that we will see, is when we think about the electrons here that's happening, it's really these 6 electrons, for example, they're coming from these 6 electrons. So it's really these 6 electrons, since I wrote it this way, being transferred over there to the cadmium in this particular case. So if you were asked, you know, what is the total number of electrons that are happening here? The number of electrons that are being transferred is actually 6 electrons, not 12. So sometimes people add them together, go, there's 12 electrons, but there's really not, because the 6 electrons are being lost from the chromium, and those same 6 electrons are going to be picked up by the cadmium here. So it's a transfer of a net total of 6 electrons. And there are going to be some equations where you'll need to basically figure out how many electrons there are being transferred. And again, you'd want to make sure you don't add up both parts of it. So this leaves us really the last thing, which is calculating the E of the cell. And again, you do have 2 options. I'm going to show you again both of them. You can choose whichever way you want. First off, since I actually changed the sign in this case, because I personally changed the sign, that means I can go with the addition version of this equation, because I already did that, which means I would take my cathode, which is the cadmium, minus 0.4 volts, plus, because I changed the sign, plus 0.74 volts, going to yield me 0.34 volts as my cell voltage. Now, if you had this problem, and the problem was just like it originally asked, it didn't really ask for all this extra stuff. We threw it in for free here. It really just wanted to know what the cell voltage was. You can definitely, and sometimes it's just easier because of that. You don't want to kind of figure out flipping things and all that kind of stuff. You can go into the subtraction version of it. And again, the importance of going into the one where you subtract is when you go to that table, you should not change the sign. So you should leave it negative 0.74. Again, that subtraction is going to change the sign like it did down here that we did manually, and it will yield you, again, the same answer. So it is your personal preference which way you want to go on that. Like I said just a moment ago, whoops, make sure you just kind of maybe choose one and stick with that same method. Any questions on how we got to any of those guys there? Okay, and then I didn't write the cell diagram. I think was the one thing I was missing. So in our cell diagram, it would look something like, again, our anode, which is our chromium. It would look something like this. You could probably assume that it's 1 molar. And our cathode would look something like this. Also maybe put 1 molar in there if you want. And our cadmium, which is a solid. Again, our anode to cathode. Any questions on the cell diagram there? Okay, then let's try another one here, see how you do. So take a moment here. Let's just calculate. We'll just do what it says. Let's go with the what is the cell voltage here in the cell. And while you're at it, why don't you also write the balance equation? We'll add just that to it, just the balance equation, this one. So write the balance equation. Okay, so let's take a look at this and see how we're doing. Again here, really not given a lot of direction in terms of, what's my anode, what's my cathode. We're not given an overall reaction that's taking place. So again, in the absence of that information, we do want to look at our Srp values, which again, these guys would come from that table. And here we see that with a positive 0.80 volts, the silver is more positive than the magnesium, and we would probably correctly assume that we should hook up the silver as our cathode, and by default that would mean that the magnesium should be our anode. So if we're going to write the balanced equation, we do need to flip around the magnesium, and the magnesium would then become magnesium going to magnesium with a +2 and 2 electrons. Our silver can remain the same, just like it's written, since it's written as a reduction reaction. We cannot add these together because we don't have the same number of electrons, so we really do need to multiply this guy by 2 to make sure that we do get our balanced equation. Also making sure that in this case, our electrons do cancel when we add them together, giving us our grand total here of 2 silver plus solid magnesium goes to magnesium with a +2 charge and silver that's solid on the other side. Again, our balanced sort of reaction is taking place in this case. Any questions on that? All right, so I'm just going to calculate E of the cell, and here I'm just going to decide to use the subtraction version of it. And what that basically means is once I identify my cathode and anode, I'm good to go. I could just put in my values. I don't have to change any signs. Again, the minus here will do that for me. And when I do all that good stuff there, we end up with 0.8 minus a minus 2.37. And it looks like a cell voltage of 3.17, I think it says. We end up with 3.17 volts. By the way, a positive voltage is always a good thing, means sort of spontaneous reaction. We'll talk about that here in just a second. But any questions on that? Again, here, if you chose to change the sign on the magnesium, which was your anode, you would have turned that into a positive 2.37, and then you would have added it to the 0.8, and you would end up obviously with the exact same answer. Any questions on sort of calculating cell voltage, writing reactions, all that kind of stuff? Okay, we're going to then sort of tie this galvanic cells and cell voltage into a thermodynamic property that we talked about before. Which is basically work and free energy. So if you remember in thermodynamics, free energy is Gibbs free energy, which is our delta G. And that's, again, basically the energy available to do some type of work. So in sort of an electrochemical process, we have those electrons really blowing out through, say, a wire and stuff like that. Again, very similar to sort of how a battery operates. It goes through, it does some type of work, kind of comes back and all that kind of stuff. And we have a relationship between sort of the cell voltage and the amount of work that can be accomplished that is related to our delta G, where basically the maximum amount of work will equal our delta G, which is, again, our free energy. So when a cell produces a current, again, that cell potential is positive, and the current, again, can be used to do some type of work, like run a motor, kind of, again, similar to when you put batteries in, it does some type of work, right? Runs your electrical devices that you put those batteries in. So let's talk about sort of that relationship between our cell voltage and delta G. We do have a few different sort of equations that do relate the two, and we'll go through these here in just a second here. I'll actually stop right here. All right, so the first one that we see is delta G is equal to minus NFE of the cell. So these are our really guys that, some of these guys that we've seen before. This is our delta G, which is our free energy, just like in thermodynamics. N is the number of moles of electrons. So that's what I was talking about a little bit earlier when we were looking at sort of those two half reactions. When we look for the number of electrons, which is sometimes referred to as N in these equations, we again want to get really the total number of electrons in the balance equation that has been transferred. So if you remember from that example we were looking at, the number of electrons is actually 6. You don't want to add up the electrons in both half reactions and use 12 in this particular case. F is Faraday's constant. It's rounded to 96,500 joules per volt per mole. And that's also sometimes a coulomb per mole, a reminder that basically a coulomb is the same as a joule over a volt. So that's sort of how we get this guy reduced down. It's basically that part of it is the C. And E of our cell is what we've been talking about. Again, whichever way you want to do it, but E of the cathode, for example, minus E of the anode. So we could use this to help us determine, is a reaction going to be spontaneous or non-spontaneous? So a second ago, I talked about that, positive cell voltage is a good thing. It's sort of a spontaneous process going to occur. And why would that be? If we look at this equation, delta G is equal to minus NFE. When we look at these two values, these guys are always going to be positive, which means the relationship between delta G and E are basically what is going to determine and what's going to happen. So if I have a positive E, that positive E and the negative that's here will turn my delta G into a negative number. And when delta G is negative, if you remember, it means the reaction is going to be spontaneous, right? So the reaction will sort of occur. Now, if I end up with a negative cell voltage, that means that when I have a negative E and the negative up in front, that's going to turn my delta G into a positive one, which means that if delta G is positive, going to be really a non-spontaneous process and not going to work. Kind of like, right, when you put your batteries in backwards, doesn't work, right? But if you flip your batteries around the right way, things work. And that's because you basically made it a non-spontaneous reaction, no electrons being generated, your electronic device not working, flip it back around, there you go. You're good to go. You're starting to produce those electrons in the proper way. And that's because, again, we can reverse the reactions, right? When we make our anode and our cathode and it doesn't work, all we simply have to do is basically just flip them around, make the guy that was the cathode the anode, the guy that was the anode the cathode, and basically that will change the sign on everybody, and that will turn our E of the cell into a negative number into a positive number in that particular case. So if you ever sort of build a galvanic cell, kind of hook it up and go, oh, I got some negative voltage, there is a very quick sort of solution to that, which means you essentially can just kind of reverse what is, the anode, what is the cathode, and you basically turn it into sort of a spontaneous process. Any questions on that equation there? Now, there's also another equation that relates, of course, we can't go too far along without talking about our good friend K, the equilibrium constant. So there is also this equation here that relates basically the equilibrium constant under equilibrium conditions and the cell voltage. And its E of the cell is equal to RT and F. Here, a couple of things. These are kind of some of the normal stuff that we anticipate. This again is our cathode minus anode. This is the gas constant, and this is the one that involves energy. So it's 8.314 joules per Kelvin per mole. T is obviously our temperature in Kelvin. N is our number of moles of electrons. And F is our Faraday's constant. And K is obviously our equilibrium constant. Now, this equation right here that I just boxed is a good one to remember. If you want, sometimes you'll see a different version of that equation, and it's at 25 degrees Celsius. What happens is these guys kind of become like constants, and you'll sometimes see two different versions of this equation. And basically, these two versions come from at 25 degrees Celsius. Kind of the natural log version, 0.0257, or 0.0592 log version, base 10 version of it. And that's the difference between those two, and why sort of the top number is a little bit different. The good news is, if you don't want to remember all those equations, you really don't need to. You could just remember this equation and just put the numbers in. Even if it's 25 degrees Celsius, just slap the numbers into that equation and you should be good to go. So what do we see in terms of relationship between sort of E and K? We see kind of the same thing. We would expect, right, a large value of K when we have a positive E of the cell, because E of the cell would indicate that the reaction is spontaneous. If the reaction is spontaneous, we would anticipate it going to the product side, and we would anticipate a large value of K, if E is positive. Obviously, the opposite would be true if E was negative. We would expect the reaction to be non-spontaneous. We would expect that the reaction would stay closer to the reactants, and we would expect that K would be on the small side. So again, it should follow our normal sort of thoughts about obviously K and which way the equilibrium should lie. Any questions on that? So again, off of this page, there's a lot of sort of formulas going, but the one there and this one here, right? These are, two really important sort of formulas that we use a lot between sort of our delta G and E and K. So the relationship that we see here is, if we have really enough information, this is our triangle here of all of our nice thermodynamics and electrochemistry sort of relationships. And we'll also see sort of the guy on the bottom there. We have seen the guy on the bottom. So we have going from, if we know delta G, we could get the E of the cell by using this relationship, and vice versa. We know E of the cell, we could use this relationship to get us to the equilibrium constant, or vice versa. And obviously this is the sort of guy that ties G and K together that we saw in thermodynamics, giving us our trifecta of wonderfulness there that ties all these guys together. Any questions on that? So as I sort of alluded to just a second ago, these things all do really sort of should tie together like we would anticipate. Again, negative delta G, meaning reactions probably spontaneous, products are favored. Products being favored means we should see a larger value of K over 1. And that should mean that the reaction is probably going to be spontaneous and that cell voltage should be positive. Again, opposite sort of effects. Positive delta G means really non-spontaneous, more reactants. More reactants means smaller K. Smaller K means probably our E of our cell is going to be negative, not much happening. Obviously, we're in that 0 range. We're pretty much sort of equally favored in each of these cases. All right, so why don't you take a second here and calculate the delta G for this reaction and determine if this reaction is going to be spontaneous under these conditions. Okay, so let's take a look. So in this particular case here, we want to calculate the delta G. We got some Srp values sort of given to us here. So clearly we want to think about sort of the equation that we just saw, which has really both of those sort of values going on here. We do need to sort of maybe calculate E of the cell, as this guy is going to be a given and a standard. We also need to figure out basically N in this particular case. So let's take a look here. First off, the N part should be pretty easy. We do see the same number of electrons in each of them. And again here, N would equal 2. It would not equal 4. So you don't want to add those together. Again, it's the total number of electrons being transferred from the anode to the cathode. Our F is our constant, which now means we really need to figure out E of the cell. In this particular case, they did give us a reaction here. And we do see the copper going from +2 to 0, which means it is getting reduced. And the iron is going from 0 to +2, which means it's getting oxidized. And we can see that then that would mean that this is our cathode and this is our anode. So we are actually looking at the equation here, not really going by necessarily the positive value that is given there. Here we would then do our E of our cell, which again is going to be our cathode minus our anode. Or again, if you want to flip the sign, you could add them together, whichever way you prefer. Here, I'm just going to kind of just go with the signs that are there and put them in correctly. 0.34 volts for my cathode minus, again, not going to flip the sign here on my anode because the subtractions there should do that for me. Going to give me a 0.78 volts. That just happened in this particular case. Any questions on that so far? At this point, we now actually do have everything that we need to calculate our delta G. Our delta G will be minus the number of moles of electrons, which is 2, times our F, which is Faraday's constant, 96,500 joules per volt per mole. And lastly, the E of the cell there that we just calculated, 0.78 volts. Volts cancel, moles cancel, leaves us with joules as actually the units we're going to end up with here. And that's going to give us 2 times 96.5 times 0.78. Gets us something like, what we got here, 150540. Again, these are joules. If you remember, delta G is typically given in kilojoules. So maybe we clean this up to about 151 kilojoules. And this obviously should be negative, as I almost forgot the negative there. And we would have negative 151 kilojoules in this case. First off, any questions on the calculation? Does all this sort of make sense? So if we look at this, what we see is we ended up with a positive cell voltage, which means the reaction should probably be heading towards the product side. And because it's heading towards the product side, we would expect it to be spontaneous in this case. We didn't calculate it here, but if we did calculate the equilibrium constant, we would expect it to be, again, probably above 1 there on the larger size in terms of value. Any questions on that there? Okay, why don't you try another one here and see what you come up with. Here's our Srp values on the bottom. We want to know in this case, will 1 molar nitric acid dissolve gold metal, so solid gold there, to form gold with a +3 charged solution? So take a couple of minutes to see what you come up with. Okay, so basically want to know, will this reaction sort of happen? Will it be spontaneous, really? So there's really a couple of things we could kind of use to help us determine that, but we could actually use sort of the equation that we were just looking at that has our delta G in there. Which means, obviously, if we hit that delta G, that's going to be negative, or our delta G that's going to be positive, non-spontaneous, or spontaneous. Also could really look at E as well, right? Our E would then also tell us that if we had a positive guy was spontaneous, non-positive is negative. So we might want to actually just start with the E, and that will help us. But let's take a look here. When we look at this, you may go, okay, we need to determine which one is our anode, which one is our cathode. And if we look at this, we got our 1.5 volts, which is more positive, bigger number there than our 0.96. And you may go, obviously, this must be our cathode, and this must be our anode. And in that particular case, you would actually be incorrect in this case. And the reason you would be incorrect is, even though they didn't give us the overall reaction, they did tell us in words sort of what is happening here. They want to know if you took nitric acid, which is HNO3, and you react it with gold metal, which is gold with no charge, will you form gold with a +3 charge? So if you simply just look at the gold part of it, by the way, this is nitric acid right there. But if you look at just the gold part of it, we see everybody here is on the wrong side, which means we technically do need to reverse the gold reaction here to get everybody on the correct side. And what that really means is the gold in this case would be the anode, and in this case, the nitric acid would be the cathode. Any questions on that? So again, it's really important not to just go on autopilot on these sort of questions where you go, okay, more positive, it's going to be my cathode 100% of the time. Definitely you can if you're not given any information, but if you're given information like in words like we were here, or in like the previous one where we were given a reaction, you do need to actually just look at the reaction and sort of see what is going on. So now that we got it sorted out correctly, our cathode and anode in this case, we really could sort of answer our question by just calculating E of our cell. Here again, I'm going to do the subtraction, which means technically speaking, we should change the sign, but I'm not going to do that. I'm just going to take the values I see in the table, which is 0.96 volts minus a 1.5 volt. That's going to yield me a negative 0.54 volts. And as I mentioned before, really at that point, I see a negative E value, which means probably going to be non-spontaneous and not occur. We could actually, take it the whole way there and verify as well, but we could put it in and our E of our cell, which is minus 0.54 volts. At this point, if we put it in, we could just see negative there and negative there, going to turn our delta G into a positive like we would expect. And both of those things will essentially tell us is this reaction will not occur here, right? Any questions on that? This is also how sometimes they will test, to see if your gold is real or not. They'll put some nitric acid on it, and your gold jewelry or something like that is still there, then it is probably real. If it kind of goes away and not so much stays and changes colors perhaps, then it's not so much real. Any questions on that there? So if you're asking about the electrons, you would want like we did in a previous example, if this is sort of your question, we would want the N value to be really the total number of electrons that have been transferred from really the cathode, from the anode to the cathode. So what I mean by that is, and if this was your question, for example, I think in a previous one, we had like 2 electrons in one and then maybe 3 electrons in the other. So what we would want to do is, like we added them together, we need to get them both to that common number of 6, right? By multiplying this guy by 3 and this one by 2. When we do that, we would end up with 6 electrons in each half reaction. And what that would mean is the N would be 6, not 12. So if that's your question, you would want to kind of balance the electrons, and then whatever that is, that balanced number is what you would use for N. Yeah. Other questions on that? Okay. All right, so why don't you give this one a go? What is the equilibrium constant for the following reaction? And let me see here. Let me give you some values that you might need. Whoops. Let's see here. Let me give you, let's see, maybe it's here. Oops. We'll go with the iron, 2 to iron here. Srp would be minus 0.44 volts. And the silver Going to our silver here, Srp value from the table, our E naught from the table is 0.8 volts. All right, so take a couple minutes here and we're looking for the equilibrium constant. So see what you come up with. Okay, so since we're getting to the end, let's take a look here. So obviously equilibrium constant mentioned. So we'd want to use obviously the equation that, involved that, which is E of our cell is equal to RT NF natural log of K. So obviously we're looking for K. R is a constant. We do have the temperature, which is 298. When we convert it, we got Faraday's constant, which is also a constant. We do need to figure out our N in this case, and we'll see what that is here in just a second. But we also do need to figure out our E of our cell, which is our cathode minus our anode. Now, you may be looking at these values and going, okay, well, clearly silver is more positive. So I think silver should be my cathode and iron should be my anode. And again, here you would be incorrect because they did give us an overall reaction here. And when we look at this overall reaction, when we look specifically, for example, at silver, silver is going from 0 to +1, which again, if you remember our little number line sort of thing, starting at 0, ending at +1 means it is actually the guy being oxidized in this case, which means in our example here, specifically because of what they gave us in the reaction, the silver is going to be the anode. And by default here, our iron is going to be the cathode as it goes from +2, it's like 0, to 0 on this side, again, gaining electrons. So again, really important to make sure that you do look at the equation to see what's going on. If we broke that off into our half reactions here, we would end up with our silver again being our anode and our iron being our cathode. We also see here in the balanced equation, the N value should equal 2 in this case. By the way, as sort of to the earlier question, if you looked up in the SRP table for silver, this is the equation that you will see. And again, here we needed to multiply this whole thing by 2 to get us the correct number of electrons, which obviously gets us the correct number of electrons to use in our sort of equation here. Any questions on that so far? Now that we got that sort of squared away, we can calculate our E of our cell. Again, I'm going to subtract, which means I'm just going to kind of throw our numbers in there. So our cathode in this case being the iron, which is minus 0.44 volts, minus, again, not going to change the sign because I am subtracting the 0.8 volts. That gives us a minus 1.24 volts, I believe. Any questions on that so far? So that would be our E of our cell. Okay, so we got now our E of our cell. We could actually put some numbers in. We could go with our minus 1.24 volts is equal to our R, which is 8.314 joules per Kelvin per mole, and our T, which is 298, converting it into Kelvin, the 25 degrees. And as we calculated is 2, and again, F is a constant 96,500 joules per volt per mole, and that's going to be the natural log of K. Doing some cleaning up on the right-hand side there, we're going to go 8.314 times 298. We're then going to divide it by 2 and also divided by 96,500. Going to get us minus 1.24 volts is equal to 0.012837 natural log of K. We're obviously going to divide that to the other side. And 1.24 negative divided by that answer gets us a minus 96.595. We'll round it to, I guess. And that equals the natural log of K. To get rid of the natural log of K, we're going to E both sides there. Again, when you do that, the natural log just cancels, giving us a K value in this case We'll call it 1.12 times 10 to the minus 42 in this case. Any questions on that calculation? So does our answers sort of make sense? Well, we saw that in this reaction, we had an E of a cell that's negative, and negative E of the cell should indicate that this reaction would technically be non-spontaneous, also have a positive delta G. And since those are all non-spontaneous positive delta G, we should be hanging out at the reactants, and we should have a small value of K, which definitely, if we take a peek over here, I would say to the minus 42 would definitely qualify as a small value of K. Any questions on any aspect of that calculation there? Okay, we'll stop here for now. We'll go to